Sometimes in life, there are too many choices to consider all possible outcomes in the time available. What we need is a way to focus on what matters. For example, if there's a ghost coming from one direction, forget all the zeros and ones, just start going in the other direction. That's your best choice right now. In math and computer science, we search for greedy approximation algorithms, processes which allow us to do a fraction of the work but still get optimal or at least near optimal results. Consider our adorable blue friend here. He has to choose between the top plate and its accompanying bag or the bottom plate and its bag. He will always choose the top plate because the available information makes that look like the better choice. However, it might not actually be the optimal choice. In this video presentation, we are examining greedy algorithms, processes which allow speedy computation with good results, despite only analyzing partial information. We want to know in what situations these greedy algorithms exist and how well they work. In other words, can we make myopic decisions and still hope for the best? One nice aspect to greedy algorithms is that it can be fairly easy to develop possible algorithms. It is also usually somewhat straightforward to calculate the big O of these algorithms. However, it can prove challenging to prove that greedy algorithms are optimal or near optimal. There are two key components to greedy algorithms. First is the greedy choice property. This means decisions are a series of locally optimal decisions. In other words, the decision that is best at the time with the data being considered. You don't look ahead, you don't backtrack and change your mind. The second component is optimal substructure. This means the optimal solution to the entire problem can be constructed by combining the optimal solutions to each step. We'll start our study of greedy algorithms by examining greedy algorithms that are computationally taxing for the human brain. Once we understand the concept with these simpler situations, we will proceed to explore other algorithms whose size can be adjusted to the point that they require greater computing needs. We will use these examples to examine how greedy algorithms are typically proven and evaluate their effectiveness compared to the optimal solution. With this foundation established, we'll continue to broaden our scope as we delve into some greedy algorithms used in approximation theory. While there are various methods involved in proving the optimality of greedy algorithms, two common methods are greedy stays ahead and the exchange method. Greedy stays ahead is really a bit of a misnomer, because we're showing that greedy is equal to optimal, not better than optimal. That would be tough to achieve. Greedy doesn't fall behind might be a more accurate name. For each step of the greedy stays ahead method, we will show that the choice made by greedy is equivalent to or as good as an optimal solution. The exchange method compares the greedy solution to an optimal solution and shows that a series of exchanges can be made that convert greedy into optimal without reducing it. Therefore, greedy is as good as optimal. Because of the incremental nature of greedy algorithms, both induction and contradiction will be your friends in constructing these proofs. Don't forget that there can be more than one optimal solution to a problem. Our greedy algorithm doesn't need to produce all the optimal solutions. We just need our greedy solution to be as good as the optimal solutions are. Consider the process of making change. There are 18 ways to give 32 cents. What mental process would you go through to make 32 cents? What criteria would you use to rate one option better than the other? 2 dimes, 2 nickels, and 2 pennies? Or maybe a quarter and 7 pennies? Or a dime, 2 nickels, and 12 pennies? Or a quarter, a nickel, and 2 pennies? This chart lists all the options available. Most people would give 1 quarter, 1 nickel, and 2 pennies. Giving change this way gives the fewest number of coins. To accomplish this, you start with the biggest coin and give as many of that coin as you can. Once you cannot do that anymore, you move on to the next largest coin and give as many of that coin as you can, and so on until you've given 32 cents in change. This process is actually a greedy algorithm. You will be giving change in the fewest number of coins possible. It turns out that this greedy change-making algorithm of giving as many coins as possible of the largest coin and working your way down is 100% optimal for American currency, along with almost every other currency in the world. As long as a larger coin is a multiple of the next smallest coin, this greedy algorithm will give you change in the fewest number of coins. You might be thinking, wait a minute, a quarter is not a multiple of a dime, it's 2.5 times the value. That's right, but it turns out our dime is completely superfluous to our greedy basis. The penny, nickel, and quarter are enough for that greedy algorithm to work. Consider instead what would happen if the nickel were removed from our currency system. Our greedy method for making change is no longer optimal. Suppose your cash register was out of nickels. How would you make 32 cents and change now? Following the algorithm, you would get 1 quarter, 0 dimes, and 7 pennies for a total of 8 coins. But 3 dimes and 2 pennies would only be 5 coins. So we see that the greedy algorithm no longer guarantees optimal results if we don't have the right basis of coins. The knapsack problem is another classic situation for greedy algorithms. Suppose you're getting ready to go on a trip. You have 45 pounds of capacity left in your suitcase, and you still want all these essential, though somewhat eclectic, items. A 6-pound frying pan, 1-pound flip-flops, your lucky gold bar, a 10-pound kettlebell, a 14-pound bowling ball, your favorite math text, and an 8-pound jug of water. Which items should you pick? This example illustrates that we can't create a greedy algorithm without knowing what the criteria for success is and how it's measured. If your goal is to have as many items as possible packed, then you start with the lightest weight options and work your way up the list. However, maybe your goal is to minimize the cost of purchasing new versions of these items at your destination. This equates to maximizing the value of what gets packed in the suitcase. We need to know the value per pound of each object, so we divide the replacement cost by the weight. Our greedy algorithm tells us to start with the most expensive item per pound, your lucky gold bar, and work your way down the list until nothing else can fit. The first 4 items weigh 37 pounds, which brings us to another key aspect of greedy algorithms. You need to know your constraints. In the case of the knapsack problem, this greedy algorithm delivers optimal results only in the fractional variant. That's the knapsack version that says taking a fractional item is okay if there isn't enough room left for the complete item. I don't know about you, but I'm going to find my 8-pound jug of water more useful than 57% of a bowling ball, unless I need a pretty doorstop wherever I'm going. The greedy algorithm for the fractional knapsack problem is optimal. We can prove its optimality with the greedy stays ahead method, because at every step we are filling the suitcase, or knapsack, with the highest value item possible. Therefore, it will never fall behind. Remember, however, that if we don't allow fractional items, we are discussing the knapsack 0-1 problem. 0 and 1 reference the binary choice that an object is either included or excluded entirely. Our greedy algorithm does not guarantee an optimal solution. Suppose you had an alphabet of 4 letters that composed messages you wanted to encode and transmit. Traditionally, each of these 4 letters would be assigned one of 4 unique 2-digit binary codes, represented by this tree. Then you would know that every 2 digits represents 1 letter, and you could encode and decode messages to your heart's content. The average letter length, which in fact is the only letter length, is 2 digits per letter. The question is, can we do better? Huffman codes propose a different structure for encoding the alphabet. Suppose that our 4 letters had a very skewed frequency distribution. Now consider this alternate tree. Instead of having 4 letters that are each 2 digits long, we now have 1 1-digit letter, 1 2-digit letter, and 2 3-digit letters. Notice that the letter with the shortest code is also the letter with the highest frequency. When we compute the average letter length, we see that 90% of the time we have a 1-digit letter, 8% of the time we have a 2-digit letter, and 2% of the time we have one of our 3-digit letters. We see that, on average, our letters will have a length of 1.12 digits, a significant reduction from the traditional scheme. You might be wondering why we didn't go for a simpler and shorter structure like the second tree on the right. The answer lies in the fact that we need to know where one letter's digits end and the next letter's digits begin, and we can no longer rely on the fact that all letters are the same length. For example, what does the message 01001 mean? Any of these words could be meant by this representation. Huffman codes solve this problem by utilizing only prefix-free trees. That means no letter string of digits is a prefix or the beginning of another letter. Each letter or character is assigned to a leaf, the end of a tree's branch. Nodes that have one or more descendants cannot be assigned letters, because their code is a prefix for all their descendants. Huffman codes are pretty interesting, but what does this have to do with greedy algorithms? It turns out we need greedy algorithms to help us figure out how to construct the best tree for a Huffman code. Here are a few of the possible tree shapes that could be utilized to assign codes to 8 letters. For each of these and other possible trees, there are 8 factorial ways to assign the 8 letters to the 8 leaves, or terminal nodes. In this tree, it doesn't matter how you assign the 8 letters, they all have the same length, so it won't affect the average letter length. However, in this tree, only 2 letters have the same length, so there are 7 factorial ways to assign the letters to the leaves of the tree that can produce a potentially different average letter length. So when you sum up all the possibilities for all the trees, you have thousands of trees to evaluate to determine the optimal choice, and that's just for 8 letters. Both the number of tree shapes and the arrangement of letters within each tree would increase rapidly, making it very difficult to compute all possibilities and determine the most efficient Huffman code. That's where greedy algorithms come to save the day. We seek a greedy algorithm that meets these criteria. We start with n letters or other characters that comprise our alphabet. With each letter, we associate its frequency. We want to assign a binary code to each letter. Not only does each letter need its own unique code, but no letter should be a prefix for any others. That way, the decoder will be certain when one letter ends and another begins. Our goal is to assign the binary codes in such a way that the average letter length is as low as possible. Initially, we start with our n letters as n independent nodes, so each letter is its own tiny little tree. We then sort the letters by frequency. Throughout this process, we will break any ties arbitrarily. With our letters sorted, we pick the 2 with the lowest frequency. We'll call those alpha and beta. We join these letters as sibling leaves in a tree with parent node P, as shown. We assign P a frequency equal to the sum of alpha and beta's frequencies. We then take this tree and insert it into the list of letters sorted by frequency, using P's frequency as our ordering criterion. The remaining iterations proceed along similar lines, with a modification that all decisions are made based on the roots of all independent trees. We select the 2 lowest frequencies, whether they belong to the singleton letter or parents of siblings. We merge them into a tree with a parent node. The new parent node's frequency is the sum of the frequencies of its 2 immediate descendants. No matter what type of elements are being merged, we add the frequencies of those elements to get the frequency for the newly created parent node. Huffman codes are an example of a proof with the exchange method. By comparing the tree of the greedy method with any other result, we'll show that greedy is better. Thus, greedy equals optimal. Repeat this step inductively for a complete proof. For each of n-1 iterations, the algorithm must find the 2 minimum values. This means the Huffman code runs in big O of n squared, which is a huge improvement over the non-greedy method. However, users who are savvy enough to utilize a heap data structure can reduce runtime further to big O of n log n. Now we move on to finding a minimum spanning tree. The quest to find minimum spanning trees brings us another classic application of greedy algorithms in graph theory. For the first cycle, we choose any vertex from the graph. We add that vertex to the set V, while E remains empty. For all future cycles, we consider all edges that have one vertex in our set V and one vertex not in V. Of those edges, we choose the edge with a minimal weight. We add this edge to our set E. We also add the vertex on the other end of the edge to our set V. We repeat this process until all vertices are in V. Our minimum spanning tree is defined by set E. We start with an arbitrary vertex. Let's say this is vertex A. So now set V contains A, while set E is still empty. Now we consider the 4 edges which bridge between V and not V. The smallest value is 7. So we choose edge AD. We add AD to E, and vertex D to our set V. We now consider edges that have A or D as one vertex and B, C, or E as the other vertex. The smallest value is 9, so we choose edge AE, adding that edge to E, and we add vertex E to set V. Now V includes A, D, and E, but not B or C. Of the edges connecting these sets, we choose DC, since it's the smallest. We add edge DC to set E, and we add vertex C to set V. For the final step, we see EB is the edge with the least weight, so we add EB to set E and vertex B to set V. The greedy algorithm is complete. We have found the minimum spanning tree for this graph. Prim's algorithm does not rely on greedy stays ahead or the exchange method, but there is still a proof for it. You start with a base case where there is a single vertex and no edge. Clearly, this is a subset of some minimum spanning tree, because minimum spanning trees include all vertices. Now assume that M is a subset of a minimum spanning tree. Select the lowest weight edge that bridges between M and not M, and add that edge to M. You can show through the cut method that M plus the new edge is still a minimum spanning tree. Another classic greedy problem is the scheduling problem, also known as interval scheduling. In this problem, you, or some resource like a shared conference room, are trying to accommodate as many events as possible. However, many events have overlapping time intervals. In other words, they conflict with each other. We call our set of all events E. Each event, E sub I, has a start time and a finish time. Our goal is to pick a schedule of non-conflicting events that incorporate the maximum possible number of events. Here we have an example with 10 events. This problem exhibits a couple key characteristics of greedy algorithms. First, it's fairly easy to come up with ideas for potential greedy algorithms. Second, while we can eliminate some potential algorithms as incorrect, proving an algorithm correct can be more challenging. Many ideas can be proposed for exploration as possible greedy algorithms for our problem. We can pick the events with the shortest duration first. We can pick the events that start the earliest. We can pick the events that finish the earliest. Or we can pick the events that have the fewest conflicts with other events. First, we explore the shortest duration algorithm. We select event 5. Then we eliminate any events which conflict with it. The shortest duration event remaining is event 10. Remember, we break ties arbitrarily. So we select it and eliminate conflicting events. Next, we select event 1. There are no conflicting events to eliminate, so we move on to select event 6, eliminating a conflicting event. Finally, we select event 7. Our schedule is complete. We can attend events 6, 5, 10, 1, and 7. Next, we explore the proposed algorithm of selecting events based on earliest start time. 2 events start at 0. I break this tie arbitrarily and pick event 8. So event 8 eliminates 3 events. Now I select my earliest remaining start time, which eliminates 1 more event. I again select the earliest remaining start time, which eliminates all remaining events. Our schedule is complete. We can attend events 8, 5, and 3. We can already tell that the earliest start time is not an optimal algorithm because the shortest duration algorithm provides a counterexample of better results. Now we move on to explore earliest stop time. The first event to finish is event 6, so we select it and eliminate events 2 and 8. The next earliest stop time is event 4, so we select it and eliminate event 5. Next, we choose event 9 and eliminate event 3. Then we choose 10, 1, and 7 with no eliminations. Our schedule is complete. We can attend events 6, 4, 9, 10, 1, and 7. We can now eliminate shortest duration as a greedy algorithm that produces optimal results. We proceed to our last possibility, fewest conflicts. First, we calculate how many other events each event conflicts with. We have a three-way tie for the least conflicts with just one. Any choice will still lead to selecting events 1, 7, and 10 while eliminating event 8. We update the conflict counts and arbitrarily choose one of the two events with only 2 conflicts. We choose event 6, eliminating events 2 and 8. We update conflicts again. Arbitrarily breaking the tie, we select event 9, eliminate event 5, and now we select event 4. Our schedule is complete. We select events 6, 4, 9, 10, 1, and 7. We note that we got the same result for the last 2 methods. This does not mean they are identical or even produce optimal results. We could try to eliminate one by creating more data sets until we find a solution in which one method is superior to the other. Ultimately, we need to prove that one, or even both, methods produces optimal results. We will focus on the earliest start time method. We can prove it by either of our 2 favorite greedy algorithm proof methods. If you want to use the exchange method, view your greedy schedule as a string of events and your optimal schedule as well. Consider the operations you would need to do to transform an optimal schedule to a greedy schedule. You can prove each operation cannot reduce the schedule based on the way you chose your greedy schedule. Once you show that the operations are sufficient to transform the optimal schedule into the greedy schedule, and that the transformations make the greedy schedule no worse than the original optimal schedule, you have proven that the optimal schedule is equal to the greedy schedule. If you would rather use the greedy stays ahead method, sort both schedules from the earliest starting event to the latest. Since the greedy schedule finishes each stage at or before the optimal schedule, you have proven that the optimal schedule is equal to the greedy schedule. As we move into approximation theory, you'll note a shift away from seeking an optimal solution through the greedy algorithms to seeking near-optimal solutions through greedy. Submodular optimization is one field of approximation theory in which greedy algorithms are useful. Suppose you inherit this oddly shaped museum containing 8 pieces of precious art. There are 4 security cameras, but they need to be updated to become functional again. Each camera covers some of the art, as shown to the right. You can only afford to update 3 of the cameras. Which 3 cameras should you update in order to maximize the number of art pieces that are protected? The submodular greedy algorithm tells us that, for each cycle, we choose the option that yields the biggest incremental gain. For cycle 1, 0 cameras are functional, so 0 pieces of art are covered. So the incremental gain for each camera is simply the number of pieces of art that it covers. Choosing the green camera would result in 2 pieces becoming protected, whereas the red would add 4 pieces of art. Therefore, we choose the red camera with an incremental gain of 4. For cycle 2, we are only interested in gains or improvements over cycle 1, so we ignore the artwork that is already in the protected set. We see that green would protect 2 additional pieces, while blue and orange would only protect 1 piece that isn't already protected. So we choose the green camera. Now the only unprotected pieces of art are numbers 2 and 7. Each of the remaining cameras would protect one of those 2 pieces of art, yielding an incremental gain of 1. We break the tie arbitrarily. Thus, the greedy algorithm gives us protection for 7 pieces with just 3 cameras. But wait a minute, that's not actually the best solution. These 3 cameras would protect all 8 pieces. So submodular optimization doesn't guarantee an optimal solution, but it does guarantee a good solution. It turns out that the greedy algorithm is guaranteed to be within a factor of 1 minus 1 over e, or about 63%, of the optimal solution. We should mention a few requirements for submodular approximation. First, the function we are using to evaluate our sets needs to be monotone. In the previous example, the function was just counting the number of art pieces. There are other options as well, such as taking the maximum. Second, submodular optimization has the property of diminishing returns. If A is a subset of B, and element X is not in B, or by extension in A, then the value of adding X to A is at least as much as the value of adding X to B. Related to submodular optimization are thresholding greedy algorithms. These methods have a threshold that must be met for the gain to be incorporated into the approximation. Consider a company that is studying anticipated increase in income from a combination of 4 possible advertising methods. The 4-way Venn diagram shows the increase expected for that combination of methods. Each method of advertising costs $2.50. Thus, we set our threshold tau to 2.5 so that the company doesn't spend more money on advertising than it makes. We start by considering the differential created by adding each method one at a time. Just using advertising method A leads to a $3 gain, while B, C, and D show gains of $4, $5, and $7 respectively. All are above the threshold. We consider the 4 numbers and pick the largest, method D. Now we see if it is worthwhile to add a second advertising method. When A is combined with D, the revenue is $8, but this is only a $1 increase from D by itself at 7. B produces a $2 incremental increase, and C has a $3 incremental increase. We'll ignore the gains below our $2.50 threshold. That leaves just one, which is automatically our largest. So we add C to our advertising plans in addition to method D. You might suspect that A and B will remain below the threshold since they were in the last round, but for the sake of our example, we'll check it again. The incremental gain of adding A to C and D is 1, as is the incremental gain of adding B to C and D. These values are below our threshold, so we ignore them. Thus, our decision is to use only methods C and D for our advertising. In threshold and greedy algorithms, each iteration consists of 2 steps, a greedy step and an approximation step. Several variations have been proposed for each one of these steps. The greedy step includes the X-greedy method, which is the most straightforward, the dual greedy, based on the concept of a norming functional, the weak greedy, where T lies between 0 and 1, and thresholding with a step delta. The Frank-Wolf algorithm also uses a greedy step. Proposed by Marguerite Frank and Philip Wolf in 1956, it lost popularity to other approximation methods, but has experienced a resurgence recently due to big data. Unlike gradient descent, which requires a projection step, the Frank-Wolf algorithm automatically stays in the feasible answer range. We note that the objective function should be Lipschitz smooth and convex. Let's do a simple example of the Frank-Wolf algorithm. Here we want to minimize f of x is equal to x minus 2 squared. First, we need to establish an interval, which we know we can use. We'll go with 0 to 4. We're also going to need the gradient. In this case, it's just 2 times x minus 2. A frequent step size chosen is 2 over k plus 2, where k is the number of the interval you're on. And we need to pick our initial guess. Let's go with x sub 0 equals 0. With our initial guess, we plug into our gradient to get negative 4. What we need to find now is the argmean of the inner product of negative 4 and t, where t is any number in our range 0 to 4. Because negative 4 is negative, we want the largest t we can get, so that would be 4, the right-hand side of our interval. We have gamma 0 is equal to 1. We plug that in to get our next x value. With an x0 of 0, x sub 1 will be 4. We move on to the next iteration. We have x sub 1 is equal to 4, so the gradient gives us positive 4. Now that we have positive 4 inside the inner product, we want t to be as small as possible, so we choose 0, the left-hand side of the interval. Our step is now 2/3, and we put everything in to get our new x value, and we get x sub 2 is equal to 4/3. Moving on to iteration 2. We plug in all of our values, and now we get x sub 3 equals 8/3. And another iteration yields that x sub 4 is equal to 8/5. Looking at the graph, you can see the x values and how they are slowly closing in on our minimum of x equals 2. Greedy approximation algorithms can be found in many fields of math. They're used to solve many NP-hard problems. They are useful for many specific applications. I hope you have enjoyed learning about greedy approximation algorithms. Please see my accompanying paper for more details. I look forward to seeing your presentations to complete our semester study of numerical analysis.